is Kiarash. I'm a master's student at Mila at the University of Montreal. Sorry that I'm not there with you in person, but today I want to present our paper called FETA-Fairness and Forced Verifying, Training and Predicting Algorithms for Neural Networks. It's a joint work with Aishwarya, Sivaraman, and Golnoosh, Farnadi from all the institutions that we're seeing down there. So I don't think we really need a motivation for fairness in this conference, but just to have something, let's take the Apple credit card application scenario, where in that application we've had cases that a male applicant would get some credit limit like 10K, but a similar female applicant would get something much less. We don't really want to see such scenarios happening. Many approaches end up optimizing an objective using SGD, like a statistical measure like group fairness. But at the end of the day, it's no consolation for an adversely affected person to say that we're fair in expectation, right? That's why we're working with individual fairness in this paper that says similar individuals should receive similar outcomes. But then the question is, what does similarity mean, right? It's a very long, open question of what we mean by similar people. So for that case, we're just gonna adopt a fairness criteria, an individual fairness criteria to defines similarity for us based on prior work. So the setup is that we have a model F, which is a binary classifier, and we have sensitive and non-sensitive attributes, and non-sensitive and S sensitive attributes. And we say that F is individually fair if and only if for all samples X and X prime, where X and X prime are similar, we have the same outcome. And similarity means the same non-sensitive attributes. So if I have the same non-sensitive attributes but different sensitive attributes, then my two individuals are similar. Like if I change race and keep everything else the same, I still want them to be similar, right? And by this definition, we also get naturally get the definition on fairness counterexamples, meaning that if we have two similar individuals that share the same non-sensitive attributes and only have possibly different sensitive attributes, if the model is predicting and giving different decisions for them, then that's a fairness counterexample. So our work has three elements. I'm going to present to you in the top-down way. The setup is that we're given a trained model. The first element is called CFAIR verification, and it just verifies and audits fairness by looking for fairness counterexamples. So we say that we have a function, let's say v, which gets f, eta, and x, and it outputs x prime, where x prime is a fairness counterexample, or null if no fairness counterexample exists, which is almost never the case. And then the other module is CFAIR prediction. This is a post-processing approach that guarantees fairness by returning the same label for all individuals sharing the same non-sensitive attribute. So it just looks for a majority vote among the group of people that share the same non-sensitive attributes and vary their sensitive attribute, and then returns that majority label. And then we have CFAIR training, which iteratively fine-tunes the model based on these counterexamples. I'm going to explain all of them in details. So this is just to have a view of the whole pipeline. We have a trained model. We get counterexample pairs from CFAIR verification. We could already apply CFAIR prediction. It's a different module, it's different than CFAIR training. We could already apply it and guarantee fairness, but in that case, we wouldn't be very accurate. Otherwise, we could apply CFAIR training, fine-tune the model a bit to be more fair, and then apply CFAIR prediction, which will give us both fairness and accuracy at the same time. So CFAIR prediction, majority voting, how do we do that? I'm going to explain it in more details later, but just to have a general view, we have, for a given test sample X, we count the number of positive and negative outcomes among individuals with the same non-sensitive but varying sensitive attributes, and then we return the majority vote. So let's say that we have a fixed set of non-sensitive attributes, and we, among the different assignments to the sensitive attributes, we see if we have positive or negative outcomes, and then we count them, and then we return the majority vote, the majority label, as the label we want for this group, so that all the people, all the individuals within this group are getting the same outcome, which means that similar individuals would get similar outcomes, and then we're guaranteeing fairness this way. CFAIR training, it kind of fine-tunes the model. It uses the counterexamples, adds them back to the training set, and iteratively continues doing this thing until the model is relatively fair. It doesn't guarantee fairness, but it helps fairness a lot. And then we could apply the CFAIR prediction which would guarantee fairness as a post-processing approach, and then we would get accuracy and fairness at the same time. But how it does it, it doesn't just get random counterexample, it gets counterexamples with maximum violation. So if we're looking for a counterexample for X, we want to maximize this guy over here, which means that in the output, in the logit output space, we want the counterexample of X, which is furthest away from X. So we want to maximize this difference in the output logit, basically. And then this is how the loss function would look like if you want to see it from a regularization point of view, but I'm not gonna dig into that details right now. Let's see some plots, and then we'll get back to some more details. So this is the experimental evaluation. These are the loss and average violation curves for fairness enforced training on different data sets. The first row shows the BCE loss, the normal binary cross entropy loss. But the second row shows the average violations. So what I mean by violations is actually this absolute difference that I just told you here. So when we're looking for maximum violations, we actually measure this difference as a violation, and then we take the average, and that gives us the average violation over the data set, for example, over our set. And that's what is being shown here. So we can see that in especially in IQMS adult, the new adult dataset, and the law school dataset, we have a sudden decrease. Like even a few iterations for these two datasets is enough to decrease unfairness significantly and not have too much violations. For German dataset, it's a bit kind of more smooth, but we don't need too many epochs of fine tuning to take into account the unfairness. Let's see some tables as well. So in the first table, we're seeing that CFAIR predictions alone, although guarantees fairness, but the cost might not be desirable. So we can see that this is the neural network baseline, a neural network trained without any fairness constraints, and this is CFAIR prediction applied on top of that neural network. So without any fine tuning, without any CFAIR training, just a post-processing majority vote, which is called CFAIR prediction, it would change flip rate to 0. And flip rate is a measure that we have for unfairness here, like the percentage of the decisions that need to be flipped for us to be fair. You can read more about it in the paper, but the good thing is that it just goes to 0, but unfortunately at a high cost of accuracy. Like, for example, for German, the accuracy cost is not so high. It's from 76 to 74. But for something like law school, it goes from 82 to 74, or for the new adult, it goes from 81 to 73, which is a lot of cost. The second table shows CFAIR training alone, although doesn't damage accuracy much, it improves fairness, but cannot guarantee. So now we have, again, the neural network base, the NNB, which is the baseline. And then we have CFAIR training. So now we are applying the fine-tuning approach, which was called CFAIR training, where we're using the counterexamples to fine-tune the model toward being fair. In that case, there is not that much damage to accuracy from 76 to 75, from 81 to 80, from 82 to 84. Actually, here we even increase accuracy, which is also something possible. And then we can see that the flip rate and CE rate, so we see improvement. Flip rate, I told you, CE rate is just a counterexample rate, the proportion of counterexamples. Again, you can see these details in the paper, but let's just say that these are measures for unfairness. We can see that they're becoming getting significantly improved, like from 24 to 2, from 89% to 15%, from 17% to 5%. But yet again, we're not actually guaranteeing it, so that's a problem. But we can apply CFAIR prediction on top of CFAIR training. So CFAIR predictions, when applied on top of CFAIR training, can provide good performance and guarantee fairness at the same time. So we can see that at the end of the day, we're not paying that much in terms of accuracy, but we're actually guaranteeing fairness. We're guaranteeing 0 flip rate, 0 counterexample rate. And we're also even seeing a decrease in inference time that we've explained more in the paper why this happens and how we've designed for this to actually happen. So like when the model is more fair, we have less inference time because we're looking for the minority label when we're counting, basically. So how do we find C's after all? So when we seek guarantees, there are two popular candidates, SMT solvers and mixed integer linear program solvers. We're using an MILP encoding, a mixed integer linear program solver based approach. We have counterexample constraints for maximizing violation, which is straightforward to implement, and we have the model constraints, which is the ReLU neural network. It's not so straightforward, but we're building on top of prior work. The works that work with SMT formulae or SMT solvers, they look something like the thing on the left, but we're using mixed integer programs. So we're adopting the work from Tijang et al., which is a mixed integer program for encoding ReLU neural networks. It's extendable to any piecewise activation function, but we're only working with ReLUs at the moment. So we have like simply the first part that simply encodes the linear affine of weights, and then we have the ReLU parts, which has binary variables that try to basically encode ReLUs. So these binary variables are associated with ReLUs. If there's 0, they mean that the state of the ReLU is inactive, and if it's 1, it means that the state of that ReLU is active. Pretty straightforward. This encoding relies on some lower bounds and upper bounds on the values of the hidden units, and we use a method by Ehlers et al. That efficiently computes these lower bounds and upper bounds. These ideas are borrowed from the neural network verification literature, and like there's a rich literature on those kind of things. But this is just to give you an idea of how things are actually happening deep down. So the shortcomings in future directions, I would say the main shortcoming of our work is that this causal discrimination fairness notion is not really causal, unlike the name. That's pretty limited. We are making a big assumption that the features are not correlated, are independent, but features may be interrelated in certain domains. So let's say if we're looking at a neighborhood of x and x prime, this is like we're looking at like a ball, and then that ball is having the hidden assumption that x1 and x2 are not correlated, which might not be the case. But in the future work that is now a preprint and an archive, we are extending to incorporate causality, and we are now considering a causal model like a simple one over here, which is x1 is just an exogenous variable, and x2 is a additive noise of the x1 and another exogenous variable. And for that, we have a different kind of neighborhood, which is like a counterfactual ball. And then we're considering that for our similarity measure. And then we're defining individual fairness, that similar individuals should receive similar outcomes on top of this new similarity measure, which takes into account the causal model and tries to overcome the shortcoming that our previous work, which is a project that I'm presenting now, has. So that's for the future work, and I guess that's it with my presentation. I guess I'm already running out of time. Just thank you for bearing with me, and sorry I'm not in person, but I think I'm gonna be online for questions. Thank you so much.